The question was, show the formation of barium chloride. How many valence electrons does barium have? Two. How many valence electrons does chlorine have? 7. What's the maximum number of electrons you can have? 8. So, this one can go over here. There's my 7. So, because one electron can go to one chlorine, barium needs to have another chlorine to take the second electron. Okay? So barium ends up, guys, barium ends up with no valence electrons. It's got an empty shell. Chlorine ends up with 8 electrons. But each one only gained 1, so the charge is 1 minus, but there's 2 of them. Hydrogen has only 1 electron. So what happens is they overlap in a region between the 2 atoms. So they're basically in the same orbit for both atoms. So that's how you would draw H2 using board diagrams. I think you would have done this in maybe grade 9 or 10? Grade 9? With oxygen, it gets a little more complicated. Because here, let's do, you have to have 4 electrons in the same region because each oxygen needs 2 more. So you have 4 electrons in the same region of space, so it gets a little crowded. So there you go, there's the 4. So, 1 bond contains 2 electrons. So for oxygen, there's going to be 2 bonds for a total of 4 electrons, yeah. So 1 bond contains, just trying to think, okay. All right, 1 bond contains 2 electrons. If there's 1 bond between 2 atoms, we call it a single bond. If there are 2 bonds between the 2 atoms, it's called a double bond. And if there's 3 bonds between the same 2 atoms, it's a triple bond. So that means a total of 6 electrons are shared between 2 atoms. You will never have a quadruple bond. The electrons just can't get close enough. Hydrogen cyanide. Smells like almonds. And you'll appreciate that for a few seconds and then you're dead. So. Okay.
Who discovered those bitter almonds?
Bitter almonds. I don't know. Probably after. Okay, so HCN. What's the combining capacity of carbon? 4. What's the combining capacity of nitrogen? 3. What's the combining capacity of hydrogen? 1. So, I'm going to teach you, I'm going to give you lessons on how to do Lewis structures. But basically, the atom with the highest combining capacity is the one in the middle. So carbon's in the middle. This is an example of a molecule that contains a triple bond. Carbon is triple bonded to nitrogen. So basically, carbon has a total of 4 valence electrons, correct? Hydrogen has 1. And then nitrogen has how many? 6 valence electrons. Nitrogen. 5. 1, 2, 3, 4, 5. So what this does for each of these atoms, guys, is it allows them to have their valence shell full. Hydrogen wants how many total? 2. So bless you. So here, your hydrogen is surrounded by 2 electrons. Carbon wants 8. So 2 and 6 more, it's surrounded by 8. Nitrogen wants how many? 8. So 6 and 2 is 8. So this is why nitrogen and carbon are going to make a triple bond, so that they complete their octet. Okay. Electronegativity. So electronegativity, we've already talked about. It's the pull on electrons that are shared by the atoms. So it's the pull on the electrons by the atoms that are sharing them. And we have this continuum that we're going to be using in order to figure out if a bond, a covalent bond, is pure nonpolar, polar, or ionic. So, do you know what a triangle means in math? Delta, or change, or difference. So, we're going to be looking at the difference in electronegativity between 2 atoms to figure out whether or not the bond is polar, meaning there's an unequal pull on electrons, or if it is nonpolar, there's no pull on the electrons. So, if The difference in electronegativity is 0. The bond is said to be pure covalent. There's 100% sharing between the two atoms. Okay? If the difference in electronegativity is between 0.5 and 1.7, the bond will be polar. If the difference in electronegativity is 1.7 or higher, it has what we call ionic characteristics, but it may or may not be ionic. You have to look at the two atoms that are involved. If it's two non-metal atoms and it ends up being greater than 1.7, they are extremely polar. It's a very polar covalent bond because it has ionic characteristics. So that leaves between 0.1 and 0.4. So this area in here. Okay? If it's 0, it's already taken. It's pure covalent. If it's 0.5, it's already taken. It's polar. That leaves between 0.1 and 0.4. If you're in here, you are non-polar. Non-polar. That means there's a little bit of a shift, but not enough to be important. This is going to be really important when we talk about whether or not a molecule is polar or not. And this will affect physical properties of substances. We're going to get into intermolecular forces, forces of attraction between molecules, and whether or not a substance is polar or not will play a big part in that. Okay, ready? This is just some background information.
Equal to 1.7, would that be ionic?
Ionic characteristics, not necessarily ionic. Okay? All right. So, halfway down the page is the definition of a covalent bond. Type of bonding which results when one or more pairs of electrons are shared between atoms in a molecule.
What's that for definition?
Right there, covalent bonding. Okay, Cl2. This is a molecular formula. A molecule of chlorine has the formula Cl2. A molecule is the smallest whole particle of that element or compound. So Cl2 is the molecular formula. Chlorine has 7 valence electrons. So it will form one bond between the two atoms. So Cl, chlorine, has 3 lone pairs. A chlorine atom has 3 lone pairs and 1 unpaired electron. It will make a bond so that that unpaired electron has a partner. So this is a Lewis structure for Cl2. You could also draw it where a short stick represents a bonding pair. And you put dots in for your lone pairs of electrons. Okay? Lone pairs of electrons, pairs of dots. This line here replaces that. So a line, one line represents 2 electrons, and these are bonding electrons. These are shared electrons between 2 atoms.
The first one's Lewis and the second one is.
Sorry? They're both blue on the second.
I don't know.
So these are 2 different Lewis structures. One shows electrons, one shows the bonding pair as a stick, okay? I prefer, when I do it, to use the second version because it's less messy. So these are both Lewis structures. These are both Lewis structures. A structural formula only shows bonds. It doesn't show lone electron pairs. So the structural formula for Cl2 is just a Cl and then a bond and then another Cl. So that's a structural formula. Okay? Yes, no? All right. So, the next part of the note is broken down by types of covalent bonds. So we're going to look at examples that have pure covalent bonding, where the difference in electronegativity is 0. Good example of these are your diatomic elements. So, the Lewis structure for H2 you could draw like that, or like that. Put 2 electrons between them, 2 dots, or 1 stick. The structural formula just shows the bonds and the atoms. And the name of this is just hydrogen. It's the element hydrogen. Oxygen. Oxygen has a combining capacity of 2. So it's going to make 2 bonds. How many valence electrons does oxygen have? 6. You've used up 2 in that bond. So it's got 4 more left to place. So there's your 4. For a total of 8. So you could draw your Lewis structure like that. Or like that. Can't really see my dots when I make them. So these electrons are spreading out so that the pairs, the lone pairs, are as spaced out as they can possibly be. So there's the Lewis structure for oxygen. Structural formula. Just remember, when you have those elements that are on the nonmetals on period 2, they want to be surrounded by a total of 8 electrons. Nitrogen. What's the combining capacity of nitrogen? 3. So it's going to have 3 bonds between it. How many total valence electrons? It has 5. How many does it want? 6. We need 2 more. So that is your Lewis structure, or there's your 5. Or there's your Lewis structure. So these molecules represent a single, a double, and then a triple bond. These are all elements, diatomic because there's 2 atoms of the same element. Any questions? So these are pure covalent because the electronegativity difference is 0. What's the electronegativity of hydrogen? Your yellow periodic table has your electronegativity values. Which number is it? 2.1. So 2.1 minus 2.1 is 0. What's the electronegativity of oxygen? 3.5. 3.5 minus 3.5 is 0. So that's how we get the difference in electronegativity. All right. Now we're going to look at a non-polar covalent bond. So CH4 is going to be our example. Okay, CH4 is your molecular formula. Carbon has the highest combining capacity of 4, so it's in the middle. Hydrogen only wants to make 1 bond. If you're an element that makes 1 bond, you're always going to be on the outside of structures. You're going to be around the outside. So Carbon has 4 electrons. Hydrogen, oops, wrong place. CH4. Carbon has 4 valence electrons. Hydrogen brings 1. So in this case, each hydrogen now has access to 2 electrons, so it's happy. And carbon has access to a total of 8, so it's filled its octet. So that is also your Lewis structure. And then structural formula just shows bonds, no lone pairs. Carbon has no lone pairs. It doesn't want lone pairs. What would you call this? Carbon, tetra, hydride. You take the second element, take off the ending, and add IDE. So carbon tetrahydride. This is also called methane. The common name for this is methane. This is produced when you are decomposing organic material and there's no oxygen present. So dumps, like the one we have up on Mountain Road, you'll see pipes coming out of the ground. And sometimes on a day like today, you'll probably be able to see it, there will be pipes coming out of the ground and you see a blue flame because they'll burn off the methane. If they didn't pipe down to the source, those piles of garbage would eventually explode because the pressure buildup from all the decaying organic matter forms this gas, and it's got to go somewhere. So sometimes what they do with garbage dumps is they take these pipes and then they heat water with the energy that is given off from the burning of this methane gas. So sometimes you'll see a blue flame, and it's so hard to see, so there's a nice shiny sunny day out there, you won't actually be able to see the color of the flame, so you won't see the flame, but you might see that haze that you see when it's hot. But smart municipalities have tapped into that energy, and they'll use it to heat some hot water, which is pretty smart. And when you toot, that's what you're tooting. You heard of Blue Angels? Boys might have. Blue Angels? No?
It's not when you like fart into the spray can or whatever.
2.1. So what is the difference? 0.4. So it falls in that area. Non-polar covalent. You don't do it 4 times. All of those bonds are the same, so they're all going to be 0.4. Okay? So that is a non-polar molecule containing non-polar bonds. All right, polar covalent bonding. So this is where there's unequal sharing, so we're going to do hydrogen chloride, HCl. Hydrogen brings 1 valence electron. Chlorine brings 7. So this way, chlorine is surrounded by its 8, hydrogen by 2. Running out of room. So you have to show the lone pairs of electrons on chlorine. The structural formula would just be H-Cl. And this is called hydrogen chloride. So, what is the electronegativity of chlorine?
Oh, chlorine is three.
Chlorine is 3. What is hydrogen? 2.1. So the difference is 0.9. So the bond between hydrogen and chlorine is polar. It's a polar covalent bond. The electrons are not equally shared. Chlorine's got a bigger pull on them than hydrogen does. So basically, hydrogen's a little bit positive, chlorine's a little bit negative. Try and keep the shape. Drew?
So the sheet always, if you were to do on the line, would that be incorrect, right? It has to be like,
Yeah, it's actually about 104 degrees. No, not 104. That's tetrahedral. It's 120 degrees.
so we know, how do you, like, is this only, like, how do you know for other compounds?
You're gonna figure it out while we do it. It's a learning process. In grade 12, we get into it deeper, but I want you to draw water in a V shape. Get used to drawing it in a V shape. I couldn't expect you to do it if I didn't tell you. So I'm telling you. Water is bent, not linear.
Is like water the only one that's bent?
No.
Like how do we know if like
Well, at this point, it's going to be, I'm going to tell you. Okay? I'd have to. All right.
Carbon is linear. Carbon dioxide is linear.
Yep, carbon dioxide is going to be linear. All right. Next one, carbon dioxide. Do you think you can draw this Lewis structure?
Yes.
Try it. If you do it in pencil, it's easier to erase.
is it gonna be a V shape too?
So we're gonna be wrong.
Could you just copy that? No V shape? Okay.
If I'm gonna be wrong.
You know what, that's not how an academic student is really learn to think, okay?
Let's see you.
Yeah.
Already done. So it's you're lucky my paper flew away. Oh, yeah, from that.
Yeah. Not too many. You're saying carbon brings a lot of electrons. It only brings 4. So are you saying that these two carbon pairs make up a certain amount of space?
What's carbon's made of electrons? Is it
If you look at this,
I am not part of this.
these two bonds
technically they're all one?
Even one of them.
They're all
Carbon's only
What
six.
you're saying, the carbon is
I literally just pressed the over. She's sitting in the show. Yeah. We're not fancy in our classic.
Carbon has four, right?
I know, but did you get the sensing when?
Oh, this is wrong, actually.
It's double bond.
No, she was saying, she gave me
Well, they're gonna be spacing me around. Split up together, and the bottom. What? Oxygen brings six. Yeah, yeah. There's some more
Does it really? There's more spectrum letters than that. That's it. Or not
what
Okay. Be teaching you how to do these, so don't sweat it if you couldn't get it. However, I am expecting you to know how to count. Carbon brings 4. Oxygen brings 6, and there's 2 oxygens, so we only have 16 electrons to play with. So it's going to look like this. Or like this. There are no lone pairs of electrons on the carbon atom. So there's nothing forcing those double bonds apart except the repulsion from the other double bonds. Because they're the same, it's going to be symmetrical. Those electrons are going to be going out to the side. When you connect your oxygen to your carbon to your oxygen, you're going to get a straight line. So this is linear. It's a straight line, yeah.
Does it matter where you place the lone pairs?
Right now, no, but they want to get as far apart as possible. So that's why I've put them kind of to the side. But if you had said they were like that, I wouldn't mark it wrong, okay? I wouldn't mark it wrong.